Okay, so this is session 4.4. We're going to talk about initial cell layouts. There's a lot of ways of doing that in CompuCell. So here we are in schedule, the last thing for day 4. So a session outline, we're going to take a quick look at some of CompuCell's built-in initializers, BlobInitializer, UniformInit, TubeInit, PolygonInit, and some demos. Talk a little bit about the PIF Initializer. Talk about manually creating cells in Python and creating cells from an image. Well, creating a field from an image, actually. There's a zip file. I put it in the chat of all the models that I'm going to be talking about. If you want to download the zip file and unzip the zip, inside the zip is the model files. I also put a link to these slides. Feel free to just listen. I mean, the demos, the demo projects have all the details in it. And it's kind of hard to keep up if you're trying to edit something as you're listening. So we'll start off with the built-in initializers, the things that Twedit has, or that you can hand code into the XML or into the Python. The first one are the UniformInitializer and BlobInitializers, which I think you've all probably seen so far. On the left is a demo of the UniformInitializer. On the right is BlobInitializer. These can both occur in the same XML file. You can use as many instances of it as you want. Here in the UniformInitializer on the left, I'm showing 4 regions. You have as many regions as you want. A region, B, C, D. And they're showed over here in the screenshot of the CompuCell output, the region A, region B, region C, D. So UniformInitializer tries to make a rectangular region with a box min and a box mat. The gap is the space between cells. So this is this A region down here. See, there's a little bit of space between every cell. There's a list of the cell types to use. If you repeat cell type names in this list, it will use that proportion for how many cells there are. So I have here a whole bunch of A cells, not quite as many B cells, and only one C cell. And C cells are probably the red ones down here. So you can, to a certain extent, control the proportion of the different types of cells. I then have another square region. CompuCell will just stack these on top of each other. So this second region overlaps of the previous region and just overwrites whatever was there. We then have a C region, which initially formed a filled box. And then the D region overwrite part of that with a box filled with medium, so to make an open area inside the box. So it's just taking advantage of the fact that CompuCell will stack the regions on top of each other, and newer regions will overwrite the previous ones. BlobInitializer is very similar, except for now, instead of giving the coordinates of the 2 corners of the rectangle, you give it a center point. So 175, 175 is about here. You then give it a radius for the big blob, not a diameter, but a radius. A gap if you want one. And so here you see there's a big gap. And then the cell widths. And then again, you can give it a list of cells and it'll populate the area with roughly that proportion of cells. So here it'd be roughly an even mix of A and B cells. We then define another region, which is just going to lay down on top of it. It's got the same center, 175, 175. It has a smaller radius and it's only the C cell type. So that's a set of red cells here in the middle. And then just to keep going, make another region off the side a little bit, give it a different radius, and fill it with just the B cells and see that it overlaps the previous cells. There's some things you have to keep track of or worry about in this when you're overlaying regions, is that older regions can clip previous regions to very small cells. You can see it in a few places here, like right here, this green cell has been partially clipped. It can get quite severe, and you could clip a cell all the way down to 1 pixel. If you're then going to assign a volume, that 1 pixel cell is going to try to grow up to its target volume, and it might distort your layout. So you kind of want to make sure you're working in some consistent offset. You know, everything is 5 pixels wide, so that when you do an overlay, you shift it 5 pixels and do more 5 pixel wide cells to try to avoid fractional cells. You could also, in your Python, just step through all your cells and delete any cell that's too small because it's been clipped because of a cell on top of it. So you do quite a bit with the blob and the slab initializers, especially with this trick of overlaying regions. The next one is the PolygonInitializer, which lets you do more complex shapes. PolygonInitializer works in 2D and 3D, but blob and slab do as well. So in the PolygonInitializer, the idea is you get a set of vertexes, an ordered vertex list, and CopperCell draws that box or that polygon, polygon, and then tries to fill it with cells. So here we're using the PolygonInitializer. We'll come back to extrude in a minute. We're doing width of 5, so our cells are 5 pixels wide. And our points there's a point at 1090, that's this point, and it goes to 1010, which is this point, and then 1010 goes to 9010, which is this point, and then 9010 goes back up to 9090, so your 9010, all the way around. And we're going to fill it with just one cell type. There's a little bit of a bug. Well, I'll go ahead and move a little bit forward. So that was the 2D initializer. In a 3D model, you can give it an extrude value, and it will just take the 2D object and stretch it into the third dimension. And it will use the same cell widths as it was using before. There's a little bit of a bug in the 2D version in that if you tell it the cells are 5 wide, your model only has a z dimension of 1. And the standard rules is it won't draw a cell if it can't fit the entire cell in the model space. So without this, I can't clip on the slide without stepping forward. Without this Zmax extrude in 2D, it won't draw any cells because no 5 pixel cell can fit into a model. It's only 1 pixel thick. But it turns out it's not very smart, and it doesn't actually know that you can tell it that there's an extrude in a 2D model. And that will let you use a 5 pixel cell, even though the thickness of the model is only 1 pixel. So it's kind of a workaround until we get that little bug fixed. But in any case, this will let you generate 2D and 3D models of any arbitrary path that you want. Of course, the fineness of your path and how many little jigs and jags it has is going to be related to how big your cells are. If you have a very complex path and really big cells, you're going to have trouble fitting cells in to fit the shape. You'll only get the cells that are completely enclosed in the path. So that's the PolygonInitializer. The next one is a TubeInitializer. And the TubeInitializer just extrudes a tube. In the TubeInitializer, you give it an inner radius. You give it an outer radius. Give it a gap, which is the distance between cells in the stack. You give it a width, which is the thickness, the gap is different, the gap between individual cells. The width is the height of each stack. So each one of these layers is 8 pixels tall. The number of slices is kind of oddly named. It's the number of cells that are placed around the ring. So here we have num slices 10. That means it's going to put 10 cells in the outer ring. Again, we have a list of cell types you want to use. You can have more than one cell type if you want. And then you give it an extrude parameter, which gives you a point in 3 dimensions to start the cylinder, a point in 3 dimensions to end the cylinder, and the cylinder will be built around that line from these 2 3-dimensional points. The cylinder does not have to be square to the model axes. You can have a cylinder running at an angle in 3D if you want. And then the final option is the shape of the cells. You need these cube cells or wedge cells. These are wedge cells. And then I use the ability to overwrite things and told it to make another cylinder inside the first cylinder. Inner radius is 0, outer radius is 9, so that it fits inside my other cylinder. Give it the same extrude coordinates, because it's going to put it inside. And it's going to use wedge-shaped shells, and it's going to use, so it's filled it with C cells, which are currently colored as red. So you can make a cylinder, you can have it hollow inside, you can have it filled inside with the same type of cells as the wall. You could fill it with another kind of cylinder. You could fill it with another kind of cylinder and then put a hole in that cylinder. you have quite a bit of flexibility for generating cylinders. Again, you can use TubeInitializer on top of Blob and Slab Initializer. Again, being careful about creating tiny little fragments of cells as you overlay specifications one on top of the other. And there's a question, yes, you can have multiple initializers. So in that very first example, both of these are in the same file. So both the call to the UniformInitializer and the call to BlobInitializer are in the same file. That's how I'm getting them all. So that's cylinders. So that gives us quite a few shapes. There's also a facility for arbitrarily defining every pixel in your model if you want. We call these PIF files or program information files, or they think it's program information files. It's not used a lot, but we do use it occasionally. So a PIF initialization file can be loaded in the XML there's a steppable command for it. You give it a file name, and it will just load it in. I'll describe the PIF file in a minute. In addition, if you're actually running CompuCell, there's a function for saving a PIF file at any point in a simulation. So you can always save a PIF file. In addition, in the XML, you can write code that every however many MCS you want, it will save a PIF file. So you can also write PIF files. This is a steppable function. So you can either, so that's two ways of creating PIF file. The third way is just to go ahead and hand roll your own. And occasionally this is needed, but hopefully you don't have to do it too often. The PIF file format is pretty simple. There's a link to the help about it. It's just a sequence of lines that have a cell number, a cell type tag, the X1 and X2 coordinates of the object, Y2, Y1, Y2, Z1, Z2. So this defines a rectangular region in 2 or 3 dimensions. So here's an example. Cell 0 is always medium. And this is creating a box that goes from X0 to X101, Y0, Y101. So just basically filled in a big box with medium. Usually you don't need to define medium, since if you don't define a pixel as something, it will default to being a pixel. But then it goes through and defines 5 cells, their type foam, and there's the coordinates of the lower left and upper right corners of the rectangular region. This is a 2D model, so all the Z coordinates are 0. It's a little bit more complicated if you're using clusters. You have to include a cluster number as well, and you have to include this magic line of include clusters. So in worst case, you could write an Excel file or a Python script or something to generate your cells, and then read them in using the standard PIF loader in your XML that I showed on the previous slide.
Jim, can you explain this again? A PIF file was introduced to one of the talks, and I don't understand why this is needed.
Well, this is a way to describe every pixel in the field in one way or another. And assign every pixel to a cell ID and a cell type. So if you imagine a CompuCell simulation, at some point you wanted to save the configuration of the simulation, you would create something like a PIF file where you say for every pixel, this pixel belongs to cell number such and such, and that cell is of type such and such.
Oh, so okay, got it. Okay, so this is just
an external format.
Yeah. Okay, so like you're calling how you want an array to be formulated, or like data to be stored. Like it looks like an array to me. And it's like over time, you're collecting data, positional data for different cell types or object types, right?
Well, this would be each PIF file would be one shot of the simulation of one particular MCS. You could have multiple PIF files, and the little command in the steppable.
Each file is only one MCS?
Is only one MCS. It's every pixel in one MCS, and giving you what cell it belongs to and what cell type that is. So this is a little bit more useful if you were trying to draw a complex shape. If you were doing segmentation external to CompuCell, and you had some histology image or something, and you did some image processing and you did segmentation, and now you have regions of interest in your image. You could write relatively easily a little chunk of code that would output that as a PIF file, and then you could read the PIF file into CompuCell. So this is just the most fundamental way you can say, well, I'm going to define every single pixel in my model, and this is a file format that will let you do that. Frequently, what you'll see done is every one of these rows will be a single pixel. So this is cell ID 1, and it's of type foam, but it's multiple pixels. It's a rectangular region. But a lot of times you'd have 50 lines for this cell ID 1 type foam, and every one of these lines would just be a single pixel. And as you can imagine, it gets very verbose in a 200 by 200 model. That's 40,000 lines in the PIF file if you do every pixel. But it's like I say, it's a brute force way of saving the data. There's better ways of doing it if you really want to save your data from site CompuCell. But this is more about an import format. So that's the PIF file. And then finally, if you can write Python, you can put pixels and cells any place you want. Whatever you want to build. If you can figure out how to code it, you can do it. So inside of Twedit, there is a helper. If you go to the CC3 Python menu, cell manipulation, there's create a cell, and there's create cell detailed. This first one is the create cell, this 2 lines of code, actually 1 line of code. It just says in the cell field, in this rectangular region of X10 to 12, Y10 to 12, place a new cell of whatever type name, whatever cell names you have in your simulation. So that'll just assign all those pixels to a new cell that you just created. That works great. The only problem with doing it this way is you don't actually know what this new cell is called. So in the detailed approach, it gives you a little bit more detail, and it goes through and says, okay, first we'll create a cell. So now we have a pointer to the cell, even though we haven't given it any pixels yet. And define an X and Y position and a size. And then you just write straight into the cell field. So this is accessing the cell field directly. And we're going to go from pixel on the X-axis from X to X plus our size, -1 or +1. It depends on how you're slicing things. And then to do the same thing with the Y-axis. It's a 2D model, so there's no Z coordinate. Z is 0. And now we're putting the cell pointer in that location, the cell pointer we created up here. The reason you'd want to do it this more complicated way is that now you actually still have your cell pointer. So now you can do cell target volume equals size times size, cell dot lambda volume equals 10 or whatever it is, and go ahead and assign your various other parameters for your cell. If you do it this way up here, you don't have that cell pointer, so you have to go and figure out what that cell created was, which is more work than it's worth. Much easier to do it this way. You can do this anytime you want. Anytime you want, you can assign any pixel to anything you want it to be, a new cell. You can assign it to another cell. So here we show, if you wanted to change the pixel at X, Y, and Z to be another cell, part of a different cell, you just point it at that other cell's ID. In addition, if you want to take a pixel and make it medium, that one's a little tricky. You'd think you might be able to say cell field equals 0, since medium is the cell ID 0, but that doesn't work because of the way the data structure works. So instead, you have to assign it to the value of none. So this basically says take this pixel region and make it medium. So that's a good way if you ever want to get rid of pixels in a cell. There's other ways of deleting an entire cell. In fact, it's up here. Here's delete cell, the delete cell ID. But this is nice if you want to carve out bits and pieces. So as I said, if you created a new cell called cell, and you assign some range of pixels in your model to that cell, now you can go in and define your target volume, lambda volume, and so forth with that cell. If you don't have all those things already assigned inside of your XML. So as an example, there's a demo, and it's also in the zip file to create this layout of cells. It basically start off with our cells are going to be 20 cells wide. Our circle width is going to be 200 pixels. And we're going to do 24 cells around the circle. And this is a little odd, but this is the list of the cell types to use just in order as it goes around the circle. That's why there's different colors. We're using 3 different cell types. I would basically just iterate over the number of cells in the circle, 24. So it's just going to count 1 to 24. It's going to calculate a rotation angle, 1/24 of 360 degrees. It's going to calculate the center of that cell using a little trig to get the angle right and offsetting it from the center of the circle. Create a new cell. So here's new cell. And this is the weirdness that we evaluate into this list of cell types. Actually get new cell to be self.newCell of, for instance, self.cell type 1. Anyway, new cell gets created and it's just iterating over this list of which cell type to be used. It then makes a box of possible pixels, square. So we iterate from X across the cell width, the box width, Y across the box height, and we check if every single pixel on that box is inside of a circle centered there. And if that pixel is inside the circle, we add that pixel to our new cell. If it's outside the pixel, outside the circle, we skip it. So we start off with a box located where we want it, and then iterate over all the pixels inside the box to figure out which ones fit inside the circle that fits inside the box. Kind of a roundabout way of making a circle, but it usually works really well. It doesn't leave any gaps in your cell. And then as before, when we're done filling all the pixels in for a particular cell, we have to remember to assign a target volume and a lambda volume for it. So this creates roundish cells, as round as you can get on a square lattice, and lays them out in a circle. One thing you have to be careful about when you're writing into the cell field is that CompuCell will not check to see if your coordinates are inside the box or not, inside of your entire model, X dimension and Y dimension and Z dimension. And in fact, it will just crash and will not tell you any useful information about why it crashed. It will just crash. So especially before you write to a pixel or reassign a pixel, you want to make sure your coordinates are within the dimensions of your model. So something like, I'm going to write ix plus 1. So I got to make sure ix is a positive number because a model width starts at 0. We don't have to check if ix plus 1 is greater than 0, since that must be true if ix is greater than 0. And then our biggest number is ix plus 1. So check and make sure it's less than the x dimension of the model. And then do the same thing for the y dimensions. Just make sure that they're within the model dimensions. You can always access the model's x dimension, the model's y dimension, and you can guess what the model's z dimension is. So always make sure that you're trying to write to a cell that actually exists in the model. So this gives you a way of, anytime you want, you can change any pixel in your model to anything else you want it to be. You can assign it to a new cell. You can set it to be a pixel of medium. You can create a new cell, put all the pixels you want into that new cell. Cells don't have to be contiguous. You can make one cell that has a bunch of pixels on one side of the model and a bunch of pixels on the other side of the model. CompuCell is not a big fan of having those fragmented cells, and it's liable to delete one of them and make the other one grow bigger. So normally you want to do contiguous regions. So we got through a whole bunch of ways to do it. Now we're going to try the last one, the most difficult one, which is trying to do it from an image. There's a demo in the visual examples that actually goes through this entire process of using a hand-drawn image. All I'm going to show is just importing an image and how you might get it into CompuCell and how you might look at it in CompuCell. So as an example, we have this little 200 by 200 pixel H&E stained image from monkey ovary. This is a secondary follicle, I think. I think I may have misnamed that. That could be a primary. There's only one layer of these darker cells around it. But the follicle is this entire region. It's multiple cells, a oocyte in the middle of it, and then various layers of cells outside of it. So what we want to do is import this image into CompuCell. By default, your CompuCell installation does not include any image processing libraries. So you'll have to import the library I use is called PIL, also called the Python image library, also just called image. So here's the commands to open up. This is an old command. I got to fix that. It's not in there anymore. But basically, you need to do a pip install of the package image or a conda activate base and then conda install image so that you have the image library. If you can figure out how to do that, there are dozens of image manipulating programs in Python. There's all kinds of things to try to find edges and normalize images and do all kinds of other things. If you'd really like to, you can import any of those image packages into the Python you're using in CompuCell. But in any case, after you get image library or PIL installed, a little bit about the PIL image library. There's another library called CV2, which is a more modern image processing library. Both of them have the ability to stretch and shrink images, crop images, rotate them, normalize the colors, convert to grayscale, all that kind of stuff. All the kind of things you'd expect an image library to be able to do. PIL in particular, although only supports bitmapped images. And doesn't work for GIF for some reason, even though GIF is a bitmap image. But most images are bitmapped, so JPEG, PNG, bitmap. If you have a different image, programs as simple as Paint can load all kinds of different image formats and save it into one of the formats that the Python image library expects. So we've got the Python image library installed into our workspace. We've got some starting image that's in a format that we can work with, the image library can work with. So in our Python, we need to import the image library. Actually, from PIL, we only import the image library. You then open an image with a file name. So now we have a PIL image called img here. The image community cannot decide where the origin of a picture is. Most image formats put the origin at the top left. So 0, 0 is the top left corner. CompuCell uses the bottom right. The image library has a function just to flip an image top to bottom, which puts the origin at the bottom left. You can then iterate over every pixel in your image. So X in range, image size 0. So this is the first dimension of the image. Y, the second dimension of the image. It's a two-dimensional image. And the pixel at X and Y is an RGB pair, a red value, a green value, and a blue value. Because this image was an RGB image. You wouldn't necessarily have RGB if it was a grayscale. You just have some gray value. So we've read the image in, and we can get the value, the RGB value for every pixel in the image. We want to do something with it. So one thing we can do is in a init function of a steppable, you can create a field. There's a line break missing here. Create a user field to store the image. So our user field is just like a diffusing field, except you have complete control over it. You can have it diffuse, you can have it not diffuse. In this case, we're just using it as a way to store a 2D array that CompuCell can actually display if you wanted to. So we get the pointer to that field. So the self field BMP image is this here. So in that field, we can address any pixel in that field. And what we're going to do is just at every X and Y that we had gotten up here in this loop, we're going to stick some value out of the image, the red value or the green value or the blue value, or we might take these three values and add them up and divide by 3. A lot of things you could do. In any case, when you're done with that, you now have a user field that you can display. The names don't show up here, but this is the sum of the RGB channel divided by 3 and divided by 255, so that all these pixels range from 0 to 1. This is the red channel. This is the green channel. I'm getting it backwards. This is the green channel. This is the blue channel. And this is the red channel. They don't look red, green, and blue because in CompuCell, we only have this one color map. which is unfortunate. If we had more color maps, we could make the red channel be all reds and the blue channels be all blue. But in any case, that image now is in CompuCell. We've got the RGB values for every pixel in the image, and we could start processing it if we wanted to. It's probably not a good idea to try too hard to do that. You certainly could. As I said, you can import any other Python library you want and do edge finding, contrast adjustment. Edge finding in particular would be something you might consider doing to see if you can find the edges that outline regions, and then use those edges to help you assign things. But I think if you're getting to that level of complexity, you're probably better off just writing a standalone Python program to do your image manipulation and to get it into something more usable in CompuCell, like write a Jupyter notebook that reads the image in, import some segmenter, have it segmented, create objects or regions of interest, and convert the regions of interest into a PIF file, and then read the PIF file into CompuCell. This is just showing kind of the key lines. Import system, because we're going to be manipulating a path. Import pill, import image. You need a path to an image. Open the image with that path. If you just print image, it'll give you information like the dimensions of the image and whether it's RGB and various other things like that, total file size, all kinds of other stuff. So we went through that all pretty quick. We talked about the built-in, Twedit's built-in initializers, Blob for doing circular-ish regions, UniformInitializer for doing rectangular slabs, TubeInitializer for cylinders, PolygonInitializers for irregular polygons, just defined by a sequence of points around a shape, which can be extruded in 3D. Talked a little bit about the PIF Initializer, which is just the absolute most fundamental way you could describe every pixel in a CompuCell simulation. Talked about manually creating cells in Python and reading cells from an image. And that zip file, I just put it in the chat again, contains all of these models that I've been showing. So every one of these models filed. And in fact, they're tagged in here in green. So this demo is in that zip file called slab blob demo. And there's a demo in there as well for reading, import image demo for reading images. So there's a question, does Pillow library work? Pill is Pillow. Pill is a real old library and it's got several different names. So it's Python image library, or Pill, or actually Pillow is a variant on Pill, or it's just called image. Any image manipulating program will work. So like I say, CV2 is a more common, a newer one for manipulating images. They all have kind of the same basic process of you basically say image and you give it an image open and it returns some numerical representation, a NumPy array, which might be 2D or 3D or 6D. It could be up to 6 dimensions if you've got RGB as a dimension. There's 3 separate dimensions. So any image library you feel comfortable with.
Jim, what's an example of when you would visualize a simulation on top of a static image, like an H&E stain?
One example would be if you were to import a set of fibers, an image of a set of fibers. You could make that set of fibers into a field and then have cells on top of that field chemotaxing to the fibers. The cells would be doing a random walk, and if they're sitting on top of a fiber find in the field, their random walk would be up and down the fiber. If they're not sitting on a fiber, then their random walk would hopefully eventually find a fiber, and once they find a fiber, they'd start chemotaxing along walking up and down the fiber. So there's a visual demo of creating fibers that might be an application of this.
Like the H&E stain, are you saying that they would go like, because the cells wouldn't know that the image is there, would they? I don't know if they would be, I didn't count. So yeah, would they move around certain structures in the H&E? Yeah, how would they?
When we're at this point, this is a cell field. excuse me, this is a CompuCell field, not a cell field. This is a CompuCell field. So this is treated by CompuCell exactly the same way that a diffusing field is. So
Okay.
a cell can sense this field.
Okay, got it. Okay.
But it's not a cell field, so a cell can walk around on top of this image here and change its behavior depending on what colors of pixels there are beneath it. It's really not beneath it. It's kind of a separate dimensional space because the cell doesn't know. There's no constraint about the cell moving. It's not a physical object in the simulation. So you could have cells try to move about based on what is in the image. But I think, like I said, if you wanted to segment this image and then convert this into a CompuCell starting model, I would do the segmentation external to CompuCell and generate something like a PIF file and then read the PIF file into CompuCell. If you did do all the work to do this segmentation in CompuCell, I would then write it as a PIF and then use another CompuCell simulation to actually simulate it. Just separate the immense amount of work it would take to segment an image and just put that into one CompuCell project and then actual running it in a separate one. Go ahead.
Whatever that image is, it's got to just be absolutely static in the real world. It wouldn't be able to move or else the model would be inaccurate.
Right, right. You could import a stack of images, and the stack of images could represent either a three-dimensional object or a time course. So you could have multiple fields here where each one of these imported user control fields is a particular time slice in your time course.
Okay, like a neuronal Z stack and like electrical current down the C stack. I don't know.
Yeah, I think if you had a neuronal Z stack, you'd create a 3D model of the neuron. Or perhaps I guess you could do, I don't know, treat an electrical signal as a CompuCell cell and have it migrate along it. That's a little weird. That's pushing it a little bit. I can see sequential time series in a in vitro assay in a micro titer plate or a cell well or something like that, where the cells are growing and proliferating or dying or moving. I see importing that Z stack as a time stack, and then you'd have various user control fields, time 0, time 10, time 50, and as your CompuCell simulation progresses, which one of those fields it's looking at could change. That's a bit of a stretch, but you never know. You never know when somebody's going to come up with some clever way of using something that no one else has ever thought about. So, as an exercise, if people want to try, go ahead and try to create a CompuCell simulation. Use Twedit and the new simulation helper, and try to create a simulation. Actually, I should have listed the 4 slides, the 4 types, because you need that kind of as the first step. Parenchyma, matrix, basement membrane, and epithelial. Make the parenchyma and matrix a thick bottom layer and just mix the two together. And then put a layer of basement membrane on top of that, and then a layer of epithelial on top of that, and then a layer of medium on top of that. So if people want to give that a try, you can use shorter names to do less typing. So a new CC3D project, let's call it demo and let it stick it wherever I've been pointing to. Default X, Y, and Z, we'll do it 2-dimension. So can you see the general simulation properties window?
Yeah.
Okay.
Yes.
So here we're going to make it periodic on X because I'm going to run my sheet horizontally and just let the sheet wrap around on itself. You pretty much always want to change the pixel range neighbor order to 3. You always want to have this number end on 1. I'll explain why on Saturday, maybe. And it doesn't matter too much if we pick, you can only pick one of these two. You can't pick them both, so it doesn't really matter which one. We're going to use both. I take it back, we're only going to use rectangular slab in this demo. So next, we do need at least one. We need the 3 cell types. So I'm going to call them parent for the parenchyma, matrix, base M for the basement membrane, and epi for the epithelials. I always got to remember to hit your last add or you forget. So we don't need that. All we need is contact and volume. We really don't need anything else. We got a simulation, double click to open everybody up. Went to the demos. Eventually, you'll probably want to fiddle around with the contact energies, get the layers to hold together. But to start with, just do our region. So we got the UniformInitializer, and remember, you can have as many regions as you want. So to start off with, I'm just going to go and make 3 of them. And Twedit was nice, and it stuck all of our cell name types into the types list. But the first one we're going to do is the parenchyma and the matrix. All is one region. We want our X's to start at the left and go all the way to the right. The model is 255 wide. No, that's not it. I think it gets a 0. We want the maximum max to be 255. And let's see, our model is 255 tall, so maybe we'll go to 100. And we'll make the cells a bit bigger with no gaps. And then we're going to do a layer of basement membrane, so we don't need these other types here. And it's also going to go from X0, X255, all the way across the model. Now it's going to start on top of this previous region, so I'm actually going to use the same number. This basement, let's make them tiny. This is a little tricky because tiny cells can be very fragile. We'll do just a 2 pixel width cell. So this will go to 102. Our basement membrane. And then finally, our third region, our epithelials. It also goes from 0 to 255. It's just going to sit on top of our previous Y, and it's going to go up, has to go up 10. And now I'm thinking about it, do I get all these right? I think so. That's okay. And I'll make these guys 10. Double check some other stuff. Really don't need to be printing out a bunch of stuff. You have to have some command in a compound, in a Python class. So it passes, says don't do anything. All right, let's see if we save it. What happens when we open it player. We find out where our typos are. That's our initial layout. Got a mixture of our green and blue, which is matrix and the parenchyma. So this is our tissue model, a very crude tissue model with both cell types. There's a set kind of cell and feeding matrix like another kind of cell. We have a basement membrane, and on top of that, we have a layer of epithelial cells. And you see if we let it run, it just is not happy. Obvious things are is because we, in the demo, we have neighbor tracker, center mass, and we have these volumes defined. And they don't match our volumes in the simulation. Put this window down here so I can find it. So let's see, we had decided that the cell width of 10, 10, and 2. So the parenchyma were 10 by 10, so they should be 100. The matrix was also 10 by 10. And our epis were also 10 by 10. But we said that the basement membrane was only 2 by 2. So its volume is 4. Now we actually have our cells defined correctly. We run it. And I don't know if you can see it. Step, 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 step. All of our little cells went away. Adhesion is overwhelming our very tiny cells. So when you have a tiny cell, sometimes you have to give the tiny cell a much bigger lambda volume, much bigger penalty for taking away one of its pixels so that a big cell can't use adhesion to overwhelm it. I'll see if that's enough there. Step, 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 step. Nope, not enough. I may not have saved it.
Jim, can you repeat what you just said about lambda with small cells?
With a very small cell, a neighbor cell can steal a pixel from it. If the neighbor cell is too small, obviously it's allowed to steal a pixel from the little cell. But on top of that, if the neighbor cell increases its contact surfaces and can decrease its contact energy from stealing a pixel from the little cell, the contact energy can drive that theft. So we got at least those two processes going, since we don't have surface in this model. A neighbor cell that's too small and has to steal a pixel from somewhere can steal it from the little cell. And if that happens too many times, the little cell vanishes. And in CompuCell, once a cell goes to volume 0, it is gone and it cannot come back. So with this little cell, we want to make sure that there's a much bigger penalty for trying to keep other cells from stealing its very limited number of pixels.
Okay.
Little cell, don't let anybody steal anything from him. Still stealing them. So the next thing we'll look at is the adhesion energies. Adhesion's energies are a little easier to read if you break them every time the first cell type changes. Makes it easier to find stuff. Right now, all of the adhesion energies are the same. Price 20 wasn't enough to make those cells survive. Okay, they're surviving. But now, since we want to get our epithelial layer and our basement membranes to hold together and hold their positions, we want to do things like the medium should never touch the parenchyma. Or in other words, the parenchyma should really not like being next to media. And then the matrix really does not like being next to the medium. And the basement membrane doesn't like being next to the medium. And only our epithelial cells like being next to medium. Then for our parenchyma, the parenchyma really doesn't want to touch the epis. Right? These green cells down here, the blue cells, the parenchymas don't want to touch the blue cells. We want to keep the basement membrane in there. The matrix is just like the epithelial cell, so it also doesn't want to touch. The matrix is like the parenchyma, it doesn't want to touch the epithelial. The basement membrane likes touching itself, it likes touching epi. Basement membrane, and finally, that's the last class. Epis like touching epis. Well, let's see if that's enough to keep our layers together. So that's working pretty well. So we turned on the periodic conditions on the x-axis. So this green cell over here has actually got some of his pixels over here. He's wrapping around. This keeps these cells from sticking into the wall because they can see the cell on the other end of the simulation. And that includes the epi. So this epi cell can see this epi over here, or that's part of the same cells. So that layer is holding together pretty well, considering we only have adhesion constraints. We only have adhesion defined and target volume defined. We don't have the surface constraint. We don't have any focal point plasticity or other links between things. So that's not bad. Now we could say, well, what if this is actually a uterine epithelial lining? Let's put an egg in it. So we can go to, I'm back in the XML, make some space for it. This is a steppable. What we want is the BlobInitializer. Unfortunately, I didn't create cells. It's always a pain to add a new cell type to a copy cell simulation because you have to go back and redo this table and you have to go back and redo target volume. So I'm going to cheat. I'm just going to make my eggs out of, let's make them out of matrix just for grins. So we're going to make a circular blob of them. And we need to get it up here somewhere. So let's put the center at, say, 200 and 125. Uh, 125. How big of a radius? 50 to 25. Just for grids, we'll give it a gap. This is supposed to be 10. And there's a gap in it, but the gap will probably immediately go away. Yeah. So we just mix and match our blob and slab initializers. We can do, it's fairly easy to do, a mixed region, either as a sphere, a circle, or as a rectangular region. It's pretty easy to put a layer on top of that, a layer on top of that. I could put a force on this and try to drive it down, but instead, just for grins, let's do this. Let's say randomly we'll delete some of these epithelial cells. And we didn't spend a lot of time figuring out the adhesion, so we'll see if the way the adhesions are now, if I delete an epithelial cell, will the epithelial layer heal itself just by stretching the cells? Or will my basement membrane or my green and blue cells escape across the epi layer that now has a hole in it? So we might do something like if so, don't do it at the first MCS step, but every 100 MCS after that, we're going to be sloppy and import random here instead of importing it to early. We're going to do if random dot random less than equal to 5. I'm going to change things a little bit. I wasn't thinking. I'm going to visit all cells of a given type.
If I'm not wrong, maybe you need to put the equals 0 or yeah.
Yep. It's a terrible place to import. Or Python will keep trying. Well, it won't import it more than once, but it'll keep deciding that it's already imported. We'll put it up with it. We need the random number generator. We don't need anything there. So if the random number is less than 0.05, we're going to go CC Python, cell manipulation, delete cell. That cell is this cell. Okay, so that should just iterate over all the epi cells and just pick a random number. And if it's less than 0.05, Net result, it should get rid of 5% of the cells, over a gazillion replicates. And it's going to do that every 100 cells. Except I got a typo somewhere. Right there. And I got an error. It says, could not find pixelTracker plugin. We need to fix Twedit so that when you do deleteCell, it warns you that you must have the pixelTracker loaded. I'll have to come back over here. And here's a good place for it. CC3M plugins. Oops, not that one. CC3M plugins. pixelTracker. Make it look pretty. Oh, already deleted some. The simulation goes so fast that well, let's not delete them quite as often. And let's not delete quite as many. Just give it time to recover after it's deleted a cell. I'm not sure if I saved.
Can you remind us of the concept of cells engulfing other cells, basically taking over pixel space?
Okay, so I don't know if you saw it there, but the cell got deleted.
Yeah, mine's been doing it, but I'm like, wait, what's causing it?
Yeah. The epi's kind of stretch because the basement membrane doesn't like touching medium. So there it went again, and see how quickly it fixes it. What I can do is it's such a fast simulation. We'll just make it display every Monte Carlo step, and that'll slow it down. Make it seem like it's going slower. Didn't save it. Yeah, I did. Trying to figure out what I was thinking about. Number of steps. Yeah, I don't think it's doing every MCS. I think it's anything. So if you go back to the basic idea of the POTS algorithm, what it will do is it picks a pixel at random in the entire cell field. If that pixel happens to be medium, it just skips it. If it's in a cell, it then looks at whether or not it's close to the edge of a cell. If it's close to the edge of a cell, it picks randomly a pixel around itself. So for instance, if you pick this pixel where my pointer is, and then it randomly picked a neighbor pixel here, it then asks the questions, what happens if I make this neighbor pixel part of this cell and steal that pixel from this cell? And it calculates the energy penalty for doing that. If this cell is too small, it really wants to steal a pixel. If this cell is too big, it really wants to give up a pixel. But on top of all of that, this is a Boltzmann distribution. So even if stealing a pixel makes the system energy go up, that's still permitted with the Boltzmann factor or probability, as long as the increase in energy is not too much. The probability of it taking a bad step is proportional to how bad this, inversely proportional to how bad the step is. So even if this energy goes up a little bit, it might still decide to steal a neighbor pixel. Well, how does it decide what the energy is for the neighbor, stealing the neighbor pixel? Well, one of them is, like I said, the target volume. What are the target volumes of the two cells, and what are their current volumes? If this cell's too big, it doesn't want to get any more pixels. If it's too small, it wants to steal a pixel. But on top of that, if you have a surface constraint, it's how does it change the surface of this cell? If it steals a pixel, it might add surface area, it might lose surface area. So it has to figure out what the surface constraint is. Imagine this blue cell up here and looking for, like right here, where there's a single pixel between this blue cell and this green cell, a single pixel high. What if this adhesion, the blue to green adhesion, was a really low number? That is, every time it adds another edge of contact, the system energy goes down a lot. This cell could steal a pixel from the red cell just so they could make contact with the green cell. and it would just be from the surface constraint, or excuse me, from the contact energy constraint, that this guy really wants to touch this guy. In this simulation, that's not true. We didn't set the J values, the adhesion values that way. But if that decrease in energy due to adhesion is big enough, it can steal a pixel from the cell. And that can happen again and again and again. And if this red cell is too small, there aren't very many chances for it to lose a pixel before it vanishes. And again, if it ever vanishes, it's gone. These big cells don't quite have that problem. If I'm trying to find it. If this green cell really wanted to touch this green cell over here, this blue cell in the middle has a lot of pixels. So if this green cell started to expand using adhesion energies towards this other green cell, this blue cell has lots of pixels to hang on to. And it eventually would just get squished out of the way. And once it got squished out of the way, it could regrow to the target volume. So you can have a lot of bad pixel steps that are actually going up in energy. But since these cells are big enough, they can tolerate those short durations of being completely wrong sized. Little cells just can't do that. They just can't lose enough times before they vanish. And so, like I say, if they ever go to zero, they can never come back.
I had an interesting example where I put the contact energy high for anything in contact with epithelium, including medium, and the epithelial cells just traveled right up across, or the, excuse me, what's my thin layer? The basement membrane traveled right past the epithelial cells just to get in contact with the medium.
Yep. And I just thought that happened so quick there. I'm trying to think of another way of doing. So we can do, I wanted to get the simulation running slower because we can go in. Remember, almost anything in the XML you can change inside of player. So we can go into contact, and it's kind of hard to find them sometimes. You kind of have to think about how the list went. This list is the same order as in the XML. So one of these, if that's basement, this would probably be, this is the medium to the epi. If that's enough. Again, it's hard for these little cells to move. They should move up, or there it goes. You saw it over here. But as soon as one of these, as soon as the red could get access to the medium, it starts to wrap up around. It's not doing it over here because the cells are too small, and it's just too improbable that it's going to do it again. So that's if we change the epi. So if we change it back, it probably won't fix itself. It did fix itself pretty darn quickly. I put the epis back to where they should be, so they dove back down to be an epithelial layer. What we could do is matrix to epi, maybe up here. So the parenchyma, which is the blue cells, if we make them really like medium, did I take it? No, I didn't. Parenchyma to medium minus 10, you need a decimal point. Oh, come on, somebody escape. There we go. Bluey.
Whoa.
So what I've told it is, remember, contact energy, higher energy is bad, lower energy is good. We're not really trying to minimize energy, we're trying to find low energy acceptable configurations. When we made the contact energy between medium and epi very negative, then the contact energy is just driving everything. It's the only thing that matters is that contact. And I'm sure if we went in and counted up the pixels of these blue cells, the number of pixels of blue has gone up significantly. These cells are much bigger than they should be, and they're fragmented like crazy. That's if we put it back where it's supposed to be. See if it's going to heal here. Nope, my delete. I saw my delete epis in there, so I deleted that cell before I could fix it. Okay, let's see. So does that a kind of a decent explanation of why you have to be careful with little cells?
Kind of, I'm still working. I need to go back to day 2 or review
Okay.
contact. Because yeah, I'm like, wait, which one is which? When it's high, it means what? When it's low.
Yeah. And the other thing is that some people will say that CompuCell does an energy minimization. That's not true. It specifically does not do an energy minimization. If you're familiar with computational chemistry, an energy minimization tries to find the lowest energy configuration of a molecule. What CompuCell is doing is, in chemistry, would be called a dynamics trajectory. You're simulating the system at a temperature other than 0. So the system does not have to find the lowest energy configuration. It just needs to find configurations that are not too bad. And that is what causes the trajectory through space. And you can always see that in CompuCell. If you just go up into your pots and say temperature 0, now it's doing a pure minimization, and it will eventually come to a stop. It may or may not be the global energy minima, but it is definitely a local energy minima. And I still have some lines squiggling, and that tells me that there are some pixel copies that do not change the energy of the system at all. The delta energy is 0 for that pixel copy. They're still getting accepted, but this system is frozen. And this temperature actually works pretty much like you would expect it, except the numerical value doesn't make any sense. But if I make it very hot, everybody acts hot. And what does acting hot mean? Acting hot means it can access higher energy states. It's not always trying to be at the lowest possible energy state. It can go into a bad state for a while, and sometimes when it goes into a bad state, that's how it can find a better good state. So in simulated annealing, which is a common method for doing parameter estimation and optimizing parameters, you cycle the temperature of the system up and down, because when you put the temperature at 0, you don't necessarily find the global minima, you find a local minima. But once you're stuck in the local minima, you can't get out. I mean, this guy, this blob, really should find this blob. But it can't, because it has to go up in energy. But if I tell it, well, the temperature is not 0, the temperature is really hot. Now everybody's moving around like crazy. You let that go for a while. It found itself. And now I come back and say, okay, now we'll go back to try and find the local minima and clean that up. So raising the temperature lets you cross energy barriers for all intents and purposes, and lets you search configurational space much quicker. But you do get weird cell shapes. You can see it in there.
So, Jim?
Yeah.
Why did you say we would always want a pixel copy of 3?
So pixel copy, the neighbor order. So let's freeze this guy. We can actually use it as an example. Clean it up. So like I say, you pick a random pixel in the simulation. If it's a media pixel, it's boring and you skip it. You pick a pixel in a cell. If it's in the middle of the cell, there aren't any neighbors around it. All the pixels around it belong to the same cell. So you skip that. Okay, now we pick this pixel right here. The neighbor order is which of these pixels around it are candidates to be chosen. And the neighbor order 1 means the pixel straight up, straight left, straight right, and straight down. So this pixel can only sense those 4 pixels. It can't sense the diagonal pixel. So it can't sense this pixel over here. It can only look up, down, left, and right. That's neighbor order 1. Neighbor order 2 fills in, and now it looks at the pixel up and left, the pixel down and left, the pixel down and right. So it looks at all 8 of the pixels around this central pixel. Neighbor order 3 goes out 1 more layer. And what the neighbor order does, in effect, is it starts to reduce how much the cells want to stick to the lattice. I'm not sure if you can change neighbor order in a simulation that's running. But at a low neighbor order, your cells will really try to be very square or very rectangular. And as you increase the neighbor order, that's easier for them to look more circular, or actually more importantly, in dense packed cells, look more like a hexagon, which is the correct shape in 2D for dense pack. So you always want to go at least neighbor order 3. It'll help the cells look rounder or more hexagonal and less square. It won't pin your cells so much to the horizontal and vertical axes of your model. The drawback is it's slower because there's more options for where a pixel can move to.
Could you, on day 2 or day 1, I was told that trying to create the structure of microvilli would be really complex. Could we use these different initializers to do that?
How big are the villi?
I don't know. I'm just thinking like intestinal lining. I don't know.
Well, the people certainly do crypts. And so on top of
Yeah.
the crypt, you have the villi. And yes, you could. I think the only limitation would be how many villi do you want? I assume a crypt has, I don't know, 1 million villi in it. So it's probably pretty tough to simulate 1 million villi. But you could certainly, generate 50 villi if you wanted to. There are a lot of ways of doing it. You could do the PolygonInitializer and do kind of a square wave, a square tooth. And then you fill that with your parenchymal cells. And then you iterate over all those parenchymal cells. And you say, every parenchymal cell that touches medium, I'm going to change into epithelium. And that gives you kind of a jagged sawtooth or square wave pattern with parenchyma covered by epithelium. So you could certainly do it. And again, the big question would be, how many villi do you want? You could certainly do 10, probably do 100. You could probably do 10 in 3D, 10 by 10, 100 in 3D, and do a 3D version of the microvilli. You might have to play a little bit with contact energies and things to keep your protuberances from collapsing down on themselves. I've lost all of my basement membrane cells. When I set the temperature up high, all those guys got deleted. Another solution to that problem, though, would be, well, if little cells are a problem, then just don't make little cells. So instead of 2 by 2, which is 4 pixels, make it 3 by 3, which is 9 pixels, which is a lot bigger, actually. And now if that's 3, this has to go up by 1, and this has to go up by 1, and my target volume now 9. And that should make them much more robust. So it should be much less likely to get one of my red cells deleted. Oh, and now why is it not? It's not. I wanted to update every. Oh, that's because I'm changing the wrong thing. There we go. Okay, this will make it go extremely slow. But now we're looking at every pixel, or every Monte Carlo step. You can see the number down here scrolling super fast. That's maybe too slow because now it doesn't want to delete a cell.
Jim, also you had, I don't know if the others got this totally. You were saying like how you could switch a cell from one type to another. Where are you doing that in this model?
So in this model, I don't. So I'm creating, when I use the slab and BlobInitializer, I'm telling it what cell types to use. What we could do So we've actually got most of the code here. Instead of deleting the cell,
Yeah, sorry, what was this code again? You're saying for the cells in epi.
my cell type numbers are, so convert it into an parenchymal cell, which is cell type 1. There's a way to do it with names that I can never remember. So instead of deleting the cells, we're going to change the cell type. Make it happen more often because try to force it to happen frequently. There one did change there. So instead of deleting that cell, I changed its cell type. So I was saying, if I was going to make a microvilli, use there's so many ways of doing it. Basically, make a square wave, and you could do that with the PolygonInitializer, or you could do it straight in CompuCell. So a region of cells that's just, looks like a castle, the top of a castle. It goes across, it goes up, goes over, goes down, goes across, goes over, goes up, and everything below that line, you make it one cell type. That's your parenchyma. And then you iterate over every cell of that type. And then you look at every one of those cells' neighbors. And if that cell has a neighbor that's medium, then you convert that cell type from parenchyma to epithelial. So it basically just goes over the top of your shape and says, okay, I made my basic shape, but everybody that's between my cells and the media above it or beside it, I want to change those into epithelial cells. Just like you can visit every cell in your simulation, you can then visit every neighbor of that cell. So I could actually, let's give it a try. Let's see. What we'll do is we'll go back over here, and in our BlobInitializer where we are creating our epis, let's make them all parenchyma. So now I got a layer on top of blue. So if you're trying to build your crypt or your microvilli or something, and so you build your surface, you got medium above it and your cells below it. What you want to do is go and convert whatever the cell layer is on top into epithelial cells based on the fact that they're next to medium. So we only want to change these blue guys up here to epis. We don't want to change these blue guys down here to epi because they don't touch medium. So what we're going to do is we're going to step over all of the blue cells, all the epis, and then we're going to visit every single neighbor of each cell. And so we will do that in the start because you probably want to change your cells before you actually start doing all this stuff. So you go to Python, visit all cells of a given type. And I think I did that as parent. Yeah. We're going to visit all the cells that are parenchyma, our tissue, subtissue type stuff. And then we're going to go another visit, and we're going to visit all cell neighbors. So cell here is cell here, and it says get the list of every cell that's adjacent to this cell. And it returns a neighbor, which is a cell pointer, just like cell. So now we have two cells. The cells we're iterating over, and this neighbor is one of the cells that touches cell. And I probably have to make sure I got the right plugins in place. For neighbor, well, neighbor is a cell. So what's it? It's going to print the ID of the cell and the surface area between the two cells. Medium is weird. Medium is not a cell. It does not have a cell. It cannot be defined as a cell. And that's what this if neighbor does, is if the cell is a neighbor, you do this stuff. If it's medium, it does this one. So what we're going to do is, something dumb like found medium equals 1. I'm just going to set a flag that we actually did find medium for this cell. And after we finish iterating over all of this cell's neighbors, what we're going to do is we're going to change the cell. And what is the neighbor type? We want it to be an epi, just type 4. And actually, there's something like, I think that would also work, which is a much better way of doing it because it's much more mnemonic than using the numbers.
Self dot the name in all caps.
So it is that, this right there.
Self dot, yes.
Yeah, so that's much better than using numbers. I can just never remember how to do it. In any case, so at the very beginning, at the start, we're going to iterate over every cell of type parent in the simulation. We're going to set a flag for this cell so you know we have not found the medium. We're going to visit every neighbor of the cell. And if you don't actually have to do anything here, if it's a neighbor is a cell, we don't do anything at all. If the neighbor is else, not a neighbor, not a cell, that means it was medium. So we set the medium flag, say, yes, this cell touched the medium. When we're done visiting all of that cell's neighbors, if we find out that it did touch the medium, now we'll switch them to epis. And I don't want to do it there because you'll never see it. That would all happen before Pixel even drew its screen, so we would never see it. So we'll do it like this. So we'll do it at multicolor step 2. We'll be able to see it, or 10. Now it's probably going to complain that I don't have the right plugins loaded. We'll see if we start it. Maybe I do this kind of. Okay, so I got my nice layer here. At step 10, I'll change to epithelial. So you build your complex shape and just don't worry about the epithelium. And the complex shape is defined because it's touching medium. You can just iterate over all of your cells and say, am I touching medium? If yes, okay, those are supposed to be epithelial cells. And now it should start deleting them. No, I was back to changing them to blue. See what they do. See if the adhesion energy is strong enough to take this guy. I did it. It sucked this parenchymal cell into the parenchyma. And it's doing it here as well. It actually works remarkably well, given that, I just wild ass guessed what the adhesion energy should be. Now, if we want, let's see, this big blob of cells is going to be diffusing. But it's such a big blob of cells, it's going to diffuse very slow. Basically the mass is very big. It's not going to move very fast. If we waited long enough, eventually it might touch our epithelial layer, but it's going to take a very long time. We could cheat it a little bit. First of all, it'll move faster if it's not so big. So let's not use a radius quite as big. And let's move it down so it's not starting quite so far away. Now it's much smaller and it's much closer. Yeah, I've never done this and haven't done this in a very long time. I try to change the My thinking is if we can assign the pot's temperature on a per cell basis, basically, cell type basis, we can essentially make these cells really hot. And if you make them really hot, the whole blob will look really jagged and everything, but it'll also start moving around a lot faster. So we can change the motility of that and get it to start walking around faster, and maybe it will get to a epithelial layer. And it's still going to be a very slow process. Now I'm trying to remember. I don't think we can change cell motility on a per cell basis without loading the right modules, and we don't have those loaded. No, we don't have it there. But this plugin, implicit motility, basically lets you set temperature, the pot's temperature for each cell type. Now, so what I'm going to do is, so everybody's going to start off at 10, and that's actually the default pots. But I want to make is green cells. Since I didn't make a new cell type, I have no choice but to do all green cells. Very hot to make this thing, to make them walk around faster. So the greens are the matrix cells. I don't want to get too hot. That didn't help any. When in doubt, make it huge and see if it explodes. No, so it's not using the intrinsic motility.
So I think Julio suggested there's a way to do it about a per cell basis in the Python.
Let's see. We'll do that in the start. So no, it doesn't seem to be doing it. Let's see. No, that's why. Matrix, no errors. So self fluctuation doesn't seem to be doing it. Well, this is definitely a case where you really just want another cell type for your egg.
Fluct ample.
Cell really should throw an error when you do a typo like that. There we go. So 10 to the 20 is too big. Yep, that works. So our guy's going to diffuse a lot faster now, but it's still doing a random walk, so it's still going to take it quite a while. And since I don't have a separate cell type specifically for this, it makes all my green cells weird. Still doing a pretty good job of fixing when it converts an epi to a parenchymal cell. It still does a pretty good job of fixing it. Eventually, though, we'll run out of epithelial cells because we're losing epithelium. Yeah, James, your comment in the notes would have each cell kind of adaptively set its own motility based on whether or not it's got the right neighbors. And that would be really good for fixing cases where a cell has drifted off and lost contact with all the other cells. It'd help it search space a lot faster at higher temperature. And that's actually probably more biological anyway. So cell amplitude works good. I wonder if I need this plugin or not. No, apparently you don't need it. It's just an intrinsic characteristic. Fluctuation amplitude. CDF. Yeah, there it is right there. Fluctuation amplitude.
I think it's interesting to see how quickly you can develop a model.
A very few number of parameters and things can make a useful model.